Welcome. In this presentation, I will guide you through the current development status of the GeoAccu hydrogen generator. The purpose of this presentation is to provide an overview of the results achieved so far, validated in practical operation, and to highlight the key technical steps of the development. As a first step, it is important to clarify why we consider the development of our own hydrogen production unit essential, and where we see the potential to achieve improved technical performance compared to currently available electrolyzers. The underlying challenges appear in several areas. During electrolysis, the generated heat is treated as a loss in most systems, even though this energy could be technically utilized. Another key aspect is material technology. We deliberately avoid membrane-based solutions as they are costly and their service life is inherently limited. The objective of this development is therefore to explore simpler, more robust, and long-term sustainable technical solutions. The design of our generator differs fundamentally from conventional solutions. For the placement of the electrolytic cells, we utilize the steel structure of the GeoAccu 2.1 self-drilling storage probe. The reason for this approach is that we want to take advantage of the benefits provided by underground installation and arrangement in this application as well. The steel housing has already been installed, and in this configuration, we are planning for an integrated power range of 25 to 35 kilowatts. In order to address the technical questions that arise during manufacturing in a controlled and cost-effective manner, we reduce the planned scale to 1/5 and build a desktop version of the system. The purpose of this model is to verify the expected efficiency, the proper fluid flow conditions, and the uniform current distribution across the cells. This allows us to clearly demonstrate that the design is capable of eliminating the so-called stray current phenomenon, which occurs when electrical current is able to flow through the electrolyte itself. The cell geometries of the desktop model were produced using three-dimensional printing, with a resin-based material that is resistant to electrochemical effects and capable of continuously withstanding an operating temperature of 60 degrees Celsius. For the internal cell design, we developed a flow geometry that uses a single inlet and a single outlet electrolyte connection to ensure identical fluid flow through every cell. This configuration is independent of the number of cells connected in series, allowing the system to maintain uniform flow conditions and stable operation in all cases. This significantly supports continuous and efficient gas separation. The electrode structure is implemented using laser-cut nickel-plated metal plates. This material choice provides favorable electrochemical properties while also enabling cost-effective local manufacturing. The scaled-up prototype is also planned to be manufactured using three-dimensional technology, with PEEK as the base material, which offers suitable mechanical and chemical stability for industrial operating environments. Before moving on to the presentation of the actual model, it is useful to briefly summarize how our development differs from the currently widespread PEM electrolyzers. Conventional PEM systems are based on membranes. These membranes simultaneously separate the gases, conduct ions, and largely determine the lifetime and cost of the system. In our approach, the cell itself does not perform the complete gas separation. The role of the cell is to ensure stable and controlled gas generation under directed flow conditions. The actual gas separation is not assigned to a single component, but is achieved through a multi-stage physical process. This includes gas-liquid separation, the removal of water content, followed by a temperature-based separation step in which oxygen condenses while hydrogen remains in the gaseous phase. Let us now turn to the presentation of the GeoAccu hydrogen generator desktop demonstration model. The central element of the model is the hydrogen generator itself, which represents a scaled-down and proportionally accurate version of the final underground installed system. The generator has an outer diameter of 140 millimeters, and in this configuration, it contains 4 electrolytic cells connected in series. Each cell operates optimally at approximately 2.2 volts, enabling stable and efficient gas generation. The design and arrangement of the electrolytic cells are specifically adapted for vertical installation. This geometry not only supports scalability, but also forms a fundamental requirement for thermal management in the later industrial implementation. The cells are immersed in a special fluid that is electrically insulating yet exhibits good thermal conductivity. This medium ensures that the heat generated during operation is evenly removed from the cell environment. The heat is transferred through the oil medium to an internal stainless steel cartridge and from there into the external cooling water circuit. This configuration simultaneously provides effective cell cooling and enables the secondary utilization of the cooling water. System operation is supported by a circulation pump and a preheating unit, ensuring continuous and uniform gas separation within the cells. The generated gas is directed into a separate gas collection chamber, where it is separated from the electrolyte and guided toward the measurement points. In the case of the desktop model, the gas volume is collected in a water displacement vessel. During operation, we record not only electrical parameters, but also measure the temperature, humidity, and composition of the outgoing gas. These data provide the basis for preliminary prototype efficiency calculations and offer direct feedback on whether the system is operating within the intended operating range. During operation, we monitor the voltage differences between the individual cells. For this test, the total system voltage is set to a round reference value, which in this case is 8 volts. This makes it easier to sum and verify the values measured across the cells. Each cell should operate at 2 volts if no leakage current is present. It can be clearly seen that all cells are operating perfectly within the same working range. In the next step, we will build a module for dehumidifying the outgoing gas, followed by the implementation of a cryogenic LOX separation unit. After commissioning this stage, it becomes possible to document both the hydrogen purity and the mass flow rate. In parallel, we are planning the integration of a proprietary gas analyzer, which will not only be used with the desktop model, but will also be capable of continuously measuring the hydrogen to oxygen ratio at a certified level in systems operating within the 20 to 50 kilowatt power range. Based on the development results achieved so far, it can be stated with confidence that we are capable of building a scaled hydrogen production system to operate alongside the GeoAku storage solution. According to current measurements and operational experience, the system is able to reach an efficiency of approximately 75 to 80% in hydrogen production. When related to the renewable energy input, the energy required for separation and system operation represents only around 4 to 5%. This energy demand can be addressed through a one-time investment and therefore does not place a continuous load on the overall energy balance. The system design is scalable and can be implemented even in the multi-megawatt power range. The heat released during operation, at approximately 50 to 60 degrees Celsius, can be recovered in the form of cooling water and reused as secondary energy, further improving the overall efficiency of the system. Thank you for your attention.